All right, good morning. So there's no assessment this week, but in the Enroll Lab session, the TA will be there. Your priority will be maybe lab number 4 about inheritance. So just for this week, there will be some activity going on in WSC. So when you drop by for TA Q&A, you're more than welcome to. So please go to WSC 105. All right, so that's the room to go to. But just in case you go to the wrong room, I will direct you. That's not a problem. So please do come. The TA will be there to help you on lab number 4. And there are 2 more assessments for the rest of the semester. The week after, we're going to have your written test number 2 first. And then the final week, we'll have your programming test number 3. It will be on schedule. And for your written test number 2, I'll release the guide and also example question as usual pretty soon. We might be able to host maybe a review session, maybe to answer your question. Or at least I can give you a link to the past review session either way. You definitely can have some walkthrough of the questions. But for your written test number 2, so please know that it's going to cover until this Wednesday. Okay, so I'm going to confirm about the exact slide you should really study until. Most likely you have to study for the CAS as well. So it doesn't hurt to really start going over the slides already for the inheritance. Okay, I'll confirm about the coverage pretty soon. Okay, maybe after our Wednesday class. And all right, any questions? And your programming test number 2, we'll start grading pretty soon. I'll definitely reach out to you about its result and feedback before your final programming test. So you definitely get some feedback for yourself. Okay. Office hour as usual, if you want to talk to me, okay, in person or if you want to make an appointment, either way. If no question, let's now do very quick recap, and then we got to talk about variable substitution today. That'll be the key word for today. Okay, very quick. So last time we actually went over about how you can use the different keywords for implementing inheritance. I just want to remind you about 3 principles. Number 1, you should really put in the superclass or parent class as many things that are going to be shared or inherited as common into the subclasses. Number 1. Number 2, in each individual subclasses, you can introduce as many unique features like a methods or attribute as you like for that particular child class. Number 3, for any methods, for example, get tuition that inherits from your parents, you can also override it to the extent that you want. These 3 things are very important. Okay, there will be some summary as well on the slides. So when you study, you will see those points too. All right, and then we spoke about visualization. So whenever you want to visualize a child object, part of it will be the expectation that's inherited from the parents. Okay, that's also something we said. And you will definitely get something in addition in each individual child classes. Premium rate versus discount rate in our example. And it's just about, when you actually put like a different resident student versus non-resident student. So you're going to call different versions of the get tuition, and they're going to execute differently, right? That's something we said last time. Just make sure you are able to trace as well. We'll also talk about dynamic type today, a little bit later. And modifiers. So that topic there is more not exactly conceptual. It's just about programming. So whenever you're declaring attributes, methods, or classes, you want to think about what would be the other parties you really want them to see your declaration. So you got different choices here. You got private, you got protected, no modifier, and public, right? These are all the 4 that we discussed last time. I also gave you some starter project to really play with. Okay, it's really up to you. And just about the example for either public or not public classes. And that's about attributes, right? We got all the 4 possibilities, right? That's also something we said in detail. You can take a look in the recording to review, okay? Any question about modifier? All right? And of course, the advice I would give to you guys would be start with everything maybe just being private, not to be shared to anybody. And then as you create maybe more subclasses for this particular class, you may want to make some of the private attributes protected instead. So that could be shared or inherited to those subclasses. That could be a nice workflow to really go with. And this is some exercise we talk about expectation. Whenever we say expectation, it really means when you say some variable, reference variable dot, what can go after that, right? So when you on the Eclipse, if you say a reference variable dot, it will usually give you a manual list about what attributes or methods you can call. right? So that's really an expectation we are talking about. What can you expect to really use this particular reference variable? Whenever you want to look up the expectation for a particular reference variable, you only look at its static type. For example, expectation for S here will be students. RS will be resident students, and RS will be non-resident students, right? So that's something the exercise we did. Got to be very sure you know how to figure out the expectation. In summary, all the three reference variables, because the student here is the parent class, both the resident students and non-resident students, they will inherit its expectation. So that's why you can see this one here is about the expectation from the student class. All three of them will have it. In addition, let's say for resident student here, which is the static type for RS. In that way, not only about the expectation from the parents, but also the additional new expectation it declares, which is about the premium rates. Similarly, for NRS, which has the non-resident students' expectation. In that way, we're going to have the parents one that's inherited, also the discount rate that's new to that particular class. So figuring out exactly the expectations is also very important. We'll do one more exercise today. Just use a different example about a smartphone. Okay. All right, so there was one part of the makeup lecture. Remember, we finished earlier last Wednesday, so you haven't got a chance. Make sure you also catch up with this part of the lecture about intuition, about polymorphism, and dynamic binding. So I wouldn't dive into the details anymore, but I wanted to just say something quick, and we'll dive deeper into it again. Whenever you have a variable assignments, the left-hand side should have the static type more like a parents, versus the right-hand side must have the static type more like a child or the parent itself. Right? So that's really what the intuition page over here is talking about. Make sure you go over that part there to really understand. Right? And that's something I will also talk about, making it more general. It's not just about parents and also subclasses. We might have multi-layer of the classes that we have to worry about. That's something we'll get into today. So if you haven't really seen this part here, make sure you do that maybe as soon as we finish the class today. This part here is so important. And then we spoke about something called dynamic binding, just about determining the dynamic types. You can see there's a table here that we did to trace about for the same variable, S. You can see the static type is actually students, but its dynamic type is going to change from maybe null into resident students or into non-resident students. So it can change as we go. Every time you're calling, let's say, S.getTuition, if you look at these two lines, okay, this line here and this line here, we're calling the same method, and the context object is also identical. However, these two lines are going to have different behavior, like calling different versions of the getTuition, because at this point right here, the dynamic type for S is resident students. It's going to use premium rates. And at this point here, the dynamic type is non-resident students. How do I know? You have to actually trace the object reassignments, like how we did it for your written test one, from the previous lecture. Okay, so make sure you also go over this one here as soon as you can, if you haven't. Question? Okay. And then just some reminder about compilation versus runtime. Whenever we talk about compilation, only look at the static one, declared. Runtime, you have to trace. Look at the dynamic type. Okay, principle. And the next two over here are just about if we somehow extend the hierarchy for a student. So we say we got two extra layers, for example, right here. So we got multi-layer. In that case, you want to think about how you can use design number 1 and 2 to really implement it. You don't necessarily have to put that into full implementation in Java, but at least get all the details understood about design number 1 and 2, since we talk about each design also very thoroughly in the lecture. So this will be the kind of question I like to put in the exam. I'll give you a little bit of hints. I like to see exactly how you understood each design. Okay? Design 1, 2, and 3, which we also spoke about. How do you apply each one of them to a new hierarchy? And this is a new running example we're going to use as well, the smartphone. All right, right here. Okay? We're going to do one exercise very soon just to figure out. But make sure you also get yourself also familiar with all the class names over here, also about the different methods. We need to understand how to call them when applicable. All right, any question? That's about a recap from last week. All right, let's now move on. Let's now do some quick exercise right away. Let's say we're given this smartphone hierarchy. Let's try to figure out the expectation, right? The range of attributes and methods callable on different static type, basically. Okay? So let's identify where they are. The first one, the blue one, let's now get to iPhone 13 Pro, which is right here. And the orange one, let's say Huawei P50 Pro, right here. Okay, that's the orange one, right here. And also we got Galaxy S21 Plus, right here. All right, so these are the three classes. So they kind of get situated in different parts of the hierarchy. We want to see exactly what their expectations are and try to see if we can figure out anything in common or anything that should distinguish from one from another. Okay. So let's start from this one here, iPhone 13 Pro. Okay. So there are different ways for you to work it out, really. But one way to do is start with this particular one and go your way, follow the arrow all the way to the top of the hierarchy, right? So what you can do is try to go this way, okay? So go up here and then go up here and see along the way what attributes and methods you can collect from all the classes, all right? So let's now take a look. So what about for this particular class? You definitely got a new one called Quick Take. Okay, so I'll just say Quick Take. That one is unique to this particular class. It's just newly introduced. And then we get to this class over here. Its parents is going to somehow inherit the FaceTime and also the Surf Web, right? It's going to have the FaceTime and then the Surf Web. Of course, the Surf Web itself is inherited from even up. And then this one here, smartphone, we already got Surf Web, also we got dial. So this is a complete range of expectations for iPhone 13 Pro. All right, okay, let's do another two quickly, okay? And for this one here, right, you're gonna go again, follow the arrow. Go here, and go here. Because you know that everything from here is going to be inherited here. Everything from here is also going to be inherited. So it's going to accumulate the expectation from all the way up. Okay. So for that one, let's see. So zoomage is a unique method. Okay. And then Huawei, nothing new. And then we go to Android. We got Skype, and then we got Surf Web. Skype, and we got Surf Web. And similarly, when we get to the top here, we also got dial. You can definitely see there's something they overlap and something they kind of don't intersect. Okay, let's do one more, and then we can summarize. And let's look at Galaxy, right here. So go up here, go up here. And of course, you got to go up here as well, which is okay. All right. So that one there, let's see. Nothing new here, but we got side sync from Samsung. So you can think about we got side sync. And then we go up, we got Skype. Let me just move a bit. Okay, let me put side sync here. And then we got Skype and Surf Web. And finally, when we get to the top right here, dial. All right, so now that's the expectation for all these three classes. And you should definitely try to really find out expectation for other classes, just in case you're asked to find out. Let's now make some quick summary. Just to start with, right here. All these are the common expectation inherited from this particular parent class. You can think about in some way, this smartphone here is more like a parent. I put in quote parent, but it should be called ancestor. We'll talk about ancestor in a moment, but ancestor like a parents, as many levels as you like. So smartphone is definitely some ancestor for iPhone 13 Pro, also an ancestor for this also an ancestor for that. So they should really have some common expectation inherited from their common ancestor. So these are the common expectation inherited from smartphone. Okay, let's see another interesting one here. If you look at, let's say, these two, you got Skype right here, right? You can see Skype actually comes from Android, right? So if you look at these two classes, this and this, they have a common ancestor right here. But Android is not a parent of iPhone 13 Pro. That's why the Skype over here does not belong to the part of the expectation for iPhone 13 Pro, right? Okay, I will write it down as well. So this one here is, Skype here is the expectation from the common ancestor, especially Android. All right, one final thing. You can see here, we got right here, for example, Quick Take right here. And also we got Zoomage right here. Right, so these are the additional, like a class child-specific methods we only introduce at that particular level. Okay, so there's one final thing to really say. Okay, that's the child-specific methods. They are not inherited, but you just introduce them at that particular child class level. It's only example here, but it really shows you many insights into how to understand about expectation. So expectation does not come out of blue. It does come from inherited expectation from all your ancestor, and then the new expectation you introduce to yourself. Okay, they all accumulate. All right, any question about this exercise here? Okay, so make sure you guys feel comfortable about doing this kind of exercise. Would be very important to really see. All right. Okay, now having this, let's now generalize it, okay? And the one I'm going to talk about will be slide number 40. It's pretty dry, lots of bullet points right here, okay? So that's slide 40 I'm going to talk about here, but let's now read up the slides. I'll just try to visualize what's happening there. But we ought to understand about ancestor and also parents, okay? These are the two terms we want to understand, and we'll do some exercise as well. All right, slide 40. When you study, make sure you study that together with the notes. Okay, I'll get to this tree-like, hierarchy-like thing. It's very general stuff. Before that, let's clarify something here. So let's say we got 3 classes right here. Just understand about extents. So let's say we got 3 classes. 1, 2, and 3 right here. And every time diagrammatically, if you say one class is pointing to another class, so the arrow direction is important. Similarly, you got this class points to this direction over here. So this corresponds to the extents you write in Java. You will see some exercise very soon for your written test number 2. Whenever you're given a particular hierarchy, so based on the extents, you should be able to somehow visualize exactly the hierarchy, like in the smartphone or in the students. Okay, that's something you'll get a chance to practice. So let's say this is Y, this is X, this is Z. Okay, so of course we say that X extends Y, and also Z extends X, direct. However, we also need to understand Z indirectly also extends Y. Somehow the extent is transitive. If you say X larger than Y, Y larger than Z, you know X larger than Z. Transitivity, right? You learned from the math earlier. Okay, I'll write it down for this one here. So what we should know is, right here, the Z indirectly extends. From our object equality lecture earlier, every class indirectly extends the object class, but you don't really write it out. It just happened, right? You have no choice. Let's now try to understand what's going on over here. Okay? We'll start with a class called A right here. Okay, let's start with somewhere in the middle. You can think about, for example, A could be maybe Huawei right here, a little bit like that. Or A could be maybe iOS over here. Or A could be even iPhone 13 Pro, anywhere, just in general. Okay? Once you fix that particular class, let's talk about relatively, or accordingly, how we define ancestor and descendants. Okay? Let's now see some bullet point here that might be useful to see definition. Okay, let's first of all see this. Let's start with the ancestor. The ancestor classes of a particular class A will be the class A itself, plus all the classes that A either directly or indirectly extends. All right? So now, let's now visualize what's going on here. By definition, the class A itself will be its ancestor, just by definition. And also, the class that A directly extends. And also, all the classes that A indirectly extends. So that means you really follow this arrow here, go all the way to the top. Right? Here. And all the way to right here. Okay? This is what we call the ancestor of A. The green one here is what we call ancestor of A. Okay, let's start with this term here. Okay, ancestor. And what is so important about ancestor? Anything we declare here is going to be inherited to its subclass. And it's going to be inherited to all the way to this subclass here. Everything here is going to be inherited to here, and everything will be also inherited to here. So A basically accumulates all the expectation along all the ancestor, right? For example, you can see that right here, Huawei P50 Pro accumulates the expectation from all the ancestor along the way. That's how we figure out, right? That's a general pattern. Let's write it down. Number one, class A accumulates the attributes and methods. And of course, I'm assuming that these methods or attributes are not private. If they're private, they're not inherited, right? That's something we learned from visibility. From now on, let's not worry about visibility. Let's assume that it works. From its ancestor. And we actually use the range of attributes and methods that you can call on A. It's called the expectation. All right, so expectation got inherited or accumulated along the way. All right, another way, let's put it a bit more formally, but which is not too bad, right? You can say that the expectation of A is going to be greater than or equal to. Usually, it should be strictly larger than, because you will always introduce a new thing in the subclass. The expectation of any ancestor. That means if I compare this class and this class over here, the expectation for this one here must be greater than or equal to than that one. Because it's going to inherit, A is going to inherit everything from here, plus there might be some additional stuff I can add. Right? That's why the larger than or equal to, at least as many. Question? Ancestor. Good? All right, guys, it's very important, so please don't be shy. If you really somehow get stuck at a certain point, simply doesn't make sense, do say that. Everything we're going to talk about from now on is going to depend on this. All right, next one. Descendants, which is kind of a symmetric notion. Okay, what does it really mean for A's descendants? It's going to be, again, A itself. And all the classes that either directly extend or indirectly extend A. Everything underneath A, basically, including A itself. So what that means, you might be wondering, does that mean A, by definition, is the ancestor and descendant of itself? Yes, for our definition. All right? Let's now go back here. And now, how do we visualize A's descendants, right? It's going to be basically A itself and then everything underneath it, basically. So you can think about right here, Huawei over here, Huawei itself and everything underneath it. It could be Android itself and everything underneath it, right? Okay, let's now write it down. And let me annotate it first. So it's going to be A itself and also everything underneath it, right? Including the classes directly extend A, and also all the classes are indirectly extending A, right? All these, right? So the pink part is called the descendants of A. Descendants. Okay, let's now also make some very similar point like before. Okay, very similar. So number one, the expectation A, right here, whatever I have as my expectation is guaranteed to be inherited to all my descendants. They should all have my traits, basically, to my descendants. All right? So that one there, we can say the expectation A is inherited to all of A's descendants. Or, for example, think about if I somehow declare method M in A. That means every class over here should have M, guaranteed. Whether or not they choose to override it, that's another story. Okay? But they will, for sure, get inherited, that version, by default. Okay, put it more mathematically. Number two, you can think about the expectation of A. Since it's going, all A's expectation will be inherited, so its descendant will have at least as many as A, because the descendants might introduce more. Less than or equal to the expectation of any descendants class. All right, right here. We're missing something here. Right? You see that? We haven't really covered everything in the hierarchy just yet. We just intended, right? So for example, let's say here, Android, this is A. Ancestor, A and smartphone. Descendants, A itself and everything underneath it. But what about these classes? So these classes are also important. They are neither ancestor nor descendants. They are also deserved in a separate category. We'll talk about them, right? So whenever you talk about any class that's neither ancestor nor descendants, you cannot say for sure what their expectation is. You cannot really like a formulate to say larger than or equal to or less than or equal to. You cannot do that. All right, I'll write it down. So for the final category, so for example, right here, and also right here. So these classes basically neither ancestor nor descendants. Okay, so these are neither ancestor nor descendants. That means expectation in general cannot be generalized. Okay? But I'll talk about exactly what I meant. It cannot be generalized a little bit later. All right, guys, any question here? Very important, right? Let me recap. Given a hierarchy can be arbitrarily big. If you fix one class as a reference class, you define accordingly the classes, ancestors, and also descendants. Ancestor will be the class itself plus all the way to the top of the hierarchy using extends keyword. Descendants will be, again, the class itself plus all the classes that inherit, that either directly or indirectly extended underneath it, basically. And then we also got classes that are neither ancestor nor descendants. What is so important about ancestor will be, ancestor got all the traits that particular class inherits from, cumulates. And also descendants, all the descendant classes will inherit the traits or expectation from this particular reference class, right? It's kind of symmetric. Okay, so make sure you kind of review this. And then let's do one exercise very quickly. Okay. So we got 1, 2, and 3. 3 classes. Okay. For the expectation, we did something very, very similar just in the beginning of today. Why don't we, I'll assign it to you as exercise. Okay. You can download the template just to do the exercise. If you still don't feel comfortable about deriving the expectation. Okay. But let's now figure out ancestor. Let's start with, let's say galaxy S21. How many ancestors? How many? Give me a number. Yeah, Josh, go ahead. How many?
3.
You are talking about 1, 2, and 3?
Yeah.
How about itself?
Oh.
Don't forget, right? It's a common mistake, all right? That's good. So 4 ancestor. So that one there is going to be Galaxy S21 itself, Samsung, and also Android, and also smartphone. Okay, I'll just write it briefly, but you see my point. All right. Okay, let's do one. Let's do one more. How about smartphone itself? How many ancestors? 1, not 0. Okay, just itself. Okay, now you guys got an idea. I'm not gonna trouble you too much. So smartphone itself. Okay, that's all good. How about descendants? Let's say here, how many descendants? 1? Okay, good. Okay, just itself. That's going to be Galaxy S21. And what would be the class that has the most descendants? Go ahead. Smartphone, because it's at the top, right? Okay, exactly. Okay, if you're at the top, everything else will be your descendants. Okay, so that one there is going to be basically all classes in the hierarchy. All right, so we'll definitely revisit this idea about expectation, ancestor, descendants, but just make sure, get yourself very familiar about this concept over here. We're going to use it when we talk about typecast on Wednesday, okay, even earlier. Okay. And then let's do some very quick exercise, very quick. And then we're going to talk about substitution rule. Okay. So this one here, I just want to do one of them just to give you some idea. Let's say this. We have 3 variables, SP1, SP2, SP3, 3 variables. And then we have static type smartphone for SP1, which is right here. We got iPhone 13 Pro static type for SP2, which is right here. Also, we got Samsung, the static type for SP3, which is right here. Right? So you can see where exactly those static types are. So now we're only playing with static type, just to see compilation issue. So now let's isolate one of them. Okay, the green one. Let's say I want to have a variable assignments. Somehow, I put a question mark over here. Okay, this question mark here, what I'm trying to say is I'm looking at this equal sign, variable assignment. I'm basically asking the question. The question is, what variable can appear on the right-hand side without compilation error? So here we got 3 candidates. We got SP1, we got SP2, and also we got SP3. So now the question is, what can we put on the right-hand side? Well, SP1 for sure, right? Because SP1, you're just assigning a variable to itself. That one seems to be like a no-brainer, for sure. I can say SP1 is assigned to SP1, or if you declare another variable with also static type smartphone, that's also fine, right? But now the question is, can we put sp2 and sp3, right? According to our discussion about the intuition for polymorphism, yes, we can do that. Because sp1 has smartphone right here. That one there is more like a general parent or ancestor for both types over here. It's the ancestor for iPhone 13 Pro. It's also ancestor for Samsung. So it is okay to put something that's descendants on the right-hand side. All right? But I'm going to write it down first, and then I'll give you some very quick intuition. And then we're going to see that a little bit more in the next page of discussion. Okay, so the answer, okay, there are two parts, A1. You're basically saying any variable whose static type is a descendants of sp1's static type can appear on the right-hand side. So I'm saying for this particular one here, as long as the static type is a descendants of smartphone, then I'll be okay. So this means I can put sp2, I can also put sp3. Okay, that's just more like a rule. A2, second part of the answer. You want to think about the equal here is what we call a substitution. Okay, I want to somehow sp1 by something else, but I know that sp1 has certain expectation. Whatever I use to really substitute for sp1, that thing over there must have at least as many expectation as sp1, intuitively. What can give you more, at least as many expectation? A descending class. All right? So we're basically saying to substitute sp1, its static type must have at least as large the expectation of, sorry, I'm just want to go here, of sp1's static type expectation. Okay, in this case, it could be either sp2, sp3, because their classes over here are simply descendants of that. And these two are guaranteed to have as many expectation as this one here, okay, as we said earlier. All right, quick question. So now what about sp2 over here, right? If I got sp2 on the left-hand side, what can I put on the right-hand side? How many choices do I have that's legitimate? Given sp1, sp2, sp3. So you got to think about what variables actually got its static type being the descendants of sp2's static type. How many descendant class do we have? sp2 has a static type iPhone 13 Pro right here. Itself has only one descendant class, which is iPhone 13 Pro itself. So that means we can only put sp2 over here. If you put sp1 or sp3, it's not going to compile. Because these two, smartphone and also Samsung, their expectation is not going to be at least as many. Okay? Let me just put here. This one is a little bit quick, but it's just first example. Okay? But we're going to talk about the general rule. Maybe that one I should really talk a little bit more over there, and then we can revisit this example later. But this one here, if you say sp2 equals sp3, it's not going to compile. If you say sp2 equals sp1, it's also not going to compile, right? All you got to check would be these two, their static types are not descendants of sp2's static type. All right, that's something you can look up in the hierarchy. Okay, So I think the next one we should really talk about this rule, but I would suggest we take a short break, about halfway, and then we'll talk about this one from scratch. Hopefully they can emphasize, okay? All right, let's now have your iClicker ready. All right, so let's now talk about the substitution rule. So the example we just did before the break, don't feel too disengaged. If you haven't really got it 100%, it takes some time to really digest. Let's now try to understand the rule for variable assignments, okay? How about we just give you a quick summary first, and then from there we can derive about how to understand it. That might be a little bit better, okay? Why don't we start with a summary right here before I even dive into this diagram here. So here is something I wouldn't say to memorize because you might memorize the wrong way. So try to see if you can make sense out of it after the explanation. But in general, if you have a variable assignments, you have some variable number 1. And also, it's assigned to some variable number 2, all right? A variable assignments. And especially in the context, there is some inheritance hierarchy in the play. Smartphone, students, or whatever, okay? So what we are really asking is the following question. It's a compilation question. Does this variable assignments, or what we call a little bit more academic. It's more like a called substitution. You can say either way. Compile. So that's the critical question we're asking. And if you remember the principle, whenever you want to judge for compilation, you only look at the static type. You only look at that. All right? So what we do is we should, number 1, look up the static type of variable number 1. Let's say static type here is type number 1, okay? Just any type. And also variable number 2 also has a static type. Let's say that's type number 2. And T1 and T2 can be the same or can be different depending on the situation. So here is the rule. It's called the rule of substitution. Of course, in the context of inheritance. If you don't really have the inheritance hierarchy in the play, you don't really have to worry about this rule. Okay? The rule is T2 here, the expectation of P2 must be larger than or equal to the expectation of T1. We have seen this before, right? Remember? This is more like a conceptual. I shouldn't say that's a formal rule in written. What this means is that T2 must be a descendant of T1. The right-hand side that you're trying to substitute for the left-hand side must have at least as many of the expectation. That's the rule. Okay? And let's try to kind of visualize this a little bit, also with a little bit more explanation. Okay? But that's a summary. And this rule over here is going to be applied in many occasions. But just understand and also remember that rule as well. So we're going to use that for many occasions. Okay? Let's now take a look at this one here. All right? Let's build from scratch. And okay, the rule of substitution, whenever we talk about this rule over here, it's really about compilation. Okay? Compilation, and then you're looking at static type. You don't have to worry about tracing the dynamic type at this point. And let's now consider this problem here. So let's say we got OA is assigned to OB, right? Like a variable 1, variable 2. OA declared to be statically A. Now we're asking, what can OB be declared into so that this substitution or variable assignment here is going to compile? We're going to figure out exactly. Okay, I'll write it down. First of all, A here is the static type of OA. The question mark over here is the static type of OB. that we want to know what will be allowed as a static type. And the question goes like this. When we have A, assignments or variable substitution, we're asking what can the question mark static type of OB be in order for this variable assignment or substitution. Let me stick to variable assignment just for now. To compile. It's the most critical question we are asking right now. What can this be in order for the variable assignments to compile? Okay. And let's now dive a little bit into the question to understand what exactly it is asking, and then we can figure out the answer. So from here, let's now try to do this. Okay, just from here. Okay. So point number one, when we say this, we are basically substitute OA by OB. That's what we are doing. Basically, we want to think about OA and OB. They might be pointing to some objects beforehand, right? Now I want OA to actually point to wherever OB is pointing to, right? That's exactly what this variable assignment is doing, right? We know that pretty well, okay? So now we want to substitute OA by OB. And the way to understand about why the rule should be the case is to think about what happens after the substitution. And this one here relates to how we explain about the intuitive case for polymorphism. That's why I said in the beginning it's very important for you to revisit that one there to supplement this. But let's focus on this one. After the substitution, we expect, let's say OA right here. If I say OA dot right here, right? What can appear after this dot? It should correspond to the expectation of OA static type, right? So here, this part over here will be exactly the expectation of OA static type, which is A. Okay, let's now highlight it just in the diagram quickly. So that would be the expectation for A. Expectation for, let me use the same blue. So that would be the expectation for A right here. We want to be sure. Whenever you actually try to call OA dot something, it should be defined by OB. So OB should be also support that expectation. Meaning that OB should have at least as many expectations as OA. That's what we want to have. Okay, so let's now write it down. So OA's expectation must be fulfilled by OB's expectation. And to be more precise, OA has the static type A. And now OB over here is what we said, question mark. And we want the expectation to be at least fulfilled. That should be at least as many. So what we have is the expectation of the question mark here should be larger than or equal to the expectation of A. How do we visualize it? If I give an A, how can I find all the classes whose expectation will be at least as many as A? Where should I go? Go down, descend this, right? Exactly, right? So guys, that's really the reasoning part over here, all right? So that means this is the part that we can go. So I'm gonna highlight it. Including A, right here. All right. So this part here will be the descendants of A, and their expectation is guaranteed to be larger than or equal to the expectation of A. Okay. Consequently, question mark must be a descendants of A. Right? That's the final conclusion. As long as the question mark over here is a descendant class of A, including A itself, then it will compile. If not, it's not going to compile. There are two cases where it's not going to compile. It's good to actually isolate them. Case number one. If they happen to be the ancestor of A's parents. So here you can see that this guy here is A's parents, right? And A's parents' ancestor will include A's parents itself. So everything here, okay? And also, anything that's neither ancestor nor descendants. That would be right here, also right here, and also right here, okay? Let's call this will be case B, and this will be case A, okay? So put it here. So A will be the ancestor of A's parents. And case B, right here, will be neither cases. Neither ancestor nor descendants. So for these two cases right here, if the question mark right here is one of these, fail to compile. Okay, I'm running out of space, but just enough. Let me recap. So this whole thing here is really talking about variable assignments. Let me do it again, okay? Whenever you have a variable assignment here, OA is declared to be A. Let's fix that. OB over here may be declared of certain type. Depending on what that type is, this equal sign here may or may not compile. Depends. Okay? The rule goes like this. You're basically substituting OA by OB. Because I know OA dot is going to expect certain things from the expectation of A. I want to be sure after this particular substitution, OB itself can support as many expectations as what OA can support. Otherwise, the substitution should not be legal. So from there, we can say that the expectation from OB should be at least as large as the expectation of A. And to really fulfill that, it's got to be either A itself or everything underneath it, because we know everything underneath it is going to accumulate the expectation. So guarantee to have at least as many for A. All right. Yeah, I think that's pretty much. And then if it's not really descendants, either it's really the ancestor for A's parents, or it's simply neither ancestor nor descendants, it's not going to compile. Okay, we got to do some exercise quickly. Guys, any questions? Any part you want me to repeat, or maybe it will take some time? Okay. Arguably, this is one of the most important pages that you want to really digest. Everything else will depend on this. Okay, let's do a little bit more example, shall we? Okay, so this will be from slide number 43 to 44. Okay, so 43 here, just text, and 44, right? You can take a look. It's really just all the cases that we just talked about substitution. So take a look. Okay, so let's now do some quick example. So now you want to whenever you're working on compilation or rule substitution, imagine that you're a compiler. You don't really want to think too much. Only look at static type. All right? So let's see this. Let's say for this one here, let's start with the first one. This one here, should it compile? Right? The way I would do it is, first of all, look up SP1, static type, iOS. Right here. So that's the static type of SP1. And then right-hand side, SP2, has iPhone SE. iPhone SE, static type of SP2. And then ask yourself this question. Is the right-hand side static type a descendant of the static type for the left-hand side? Is it? Yes, compiles. As easy as that. This is a descending class of that, so it will compile. And the way to justify is it compiles because the static type of SP2, which is iPhone SE, is a descendant of the static type of SP1, which we know is iOS. Okay? Another way you can say, which is equivalently, which is kind of equivalent. Another way, you can also say, you can say the SP2's static type can fulfill the expectation of SP1's static type. Okay? So SP2 static type is iPhone SE. Can iPhone SE fulfill the expectation for iOS? Yes, because it's a subclass of that. Right? And this one here, you can justify by the same reason. This one also compile. I'll leave that to you. So you want to try to see, judge in the green flavor or the orange flavor. They are both equally good. Okay, but understand about each of these. Either try to come from the subclass or descending class point of view, or try to look at from the fulfilling expectation point of view. Either way. All right. And this one here. How about this one here? Does it compile? Daniel?
Doesn't compile.
Because? Spot on. Exactly. All right. So this one here, let's look at it quickly. SP2 has static type smartphone right here. SP2's static type. And then we got SP1, static type iOS. Static type of SP1. So now we're asking whether smartphone is a descendant class of iOS. No. So, fail to compile. Fail to compile. All right. All right, next one here. Okay, just a little bit more to it. Says, let's now see exactly how, well, we're now changing the topic a little bit. Well, extending it. The variable substitution now, we can now try to see how we can use it and try to do some object initialization or change the dynamic type. So let's say if I declare students statically as S. This is again the static type. So now I want to initialize S to be something that's not null. So now what can appear on the right-hand side? Okay, similar rule. The right-hand side can be any class as long as it can fulfill the expectation of students. This will be the new dynamic type for S. This will be valid if resident students can fulfill the expectation of this S static type, of the static type of S, which is students. So we're basically asking, can resident students fulfill students? Yes, because resident student is a subclass of student, or descendant class in general. All right. And we got to do some tracing. Okay. Let's see over here. I think we have done something kind of similar to this when we talk about dynamic type intuition. Let's do a little bit quick tracing here. So first of all, let's judge to see. This variable assignment here is going to compile because resident students is a descendant class of students. Because RS is a descendants of students. Similarly, this one here should also compile, right? Because non-resident students over here compiles because non-resident students is a descendants of the student class. And student class is always the static type for gym, always. Okay, right here. All right, so just make sure you can also apply the rule of substitution here. And then I'll do some tracing maybe a little bit later. There's a similar example coming. Okay. All right. Guys, how about this one here? Can you write such object initialization in Java? Can you? This one here. Would it compile? No. All right. How come? Yeah. Give us a quick check. Yeah, or we put it out. Yeah, that's right. Or you say it's not a descendant class of that, right? That's why you fell. Very good. Okay, simple, but just want to be sure. All right. So this one here, not going to compile. So hopefully you kind of get a feel about exactly where we're heading to. Just got to make sure you also review the stuff before Wednesday. Okay. Fail to compile. Because the students is not a descendants of resident student. And think about it a little bit more. The student here is the dynamic type we are proposing. Proposed dynamic type. But it's not going to be valid because the declared static type right here has the expectation that it cannot fulfill. For example, premium rates. A student cannot fulfill premium rate. So this is a static type of Jeremy. All right, good. Okay, so I think I'll leave this exercise for you. You can also give it a try. Okay, but this one very quick. I'll hand wave a little bit. Android is here. Now the right hand side is either Huawei 50 Pro, is a descendant class, seems to be okay. Galaxy S21, right here, also descendant class, also fine. Right? So we seem to be good conceptually, but I would suggest download this page or at least try and write down some explanation like how I did it earlier so you would know how to write later in the test or in the exam. Okay, I'll leave that to you. Okay, this one is similar. You can also give it a try. Okay, so let's now do some quick tracing right here. Okay, and then we can move on to define some terms. Let me just see here. Give me one moment. Okay, this one here. This one, this one. Okay, good. Let's now do this one here. Okay. Let's now try to look at, so you can see resident students, when they are the same, now you can see why the rule also work. This resident student is a descendant class of itself by definition. So that will compile. Okay. So now let's say after this. Line number 1, line number 2, line number 3. Okay, so we basically got Jin points to some students' objects. Okay, that's after number 1. After number 2, we actually got RS points to a resident students' objects. Okay, so that's number 2. Number 3, NRS points to NRS object. NRS object. All right. And then let's now see this. Should this compile? First of all, look at static type, right? RS static type, resident students. Jim, static type, students. Is this a descendant class of that? Yes, compiles, all right? So that one there is actually going to, let me say number 4. It's going to change Jim from here to RS. Okay, we agree with that. So now, let's now do some quick annotation. After this initial point, after 1, you can see that Jim is pointing to this particular objects. So student is dynamic type. Dynamic type of Jim is students. Okay, let's highlight this one. We're going to contrast. Let's focus on Jim. What about after executing this orange one? So you can see Jim right now is pointing to RS. Dynamic type changed, right? So now at this point, dynamic type of Jim. Something I want to point out to you. When I did this variable assignments, Jim is assigned to RS. Dynamic type of Jim is now changing to the dynamic type of RS because now they point to the same objects. Of course, dynamic type should be the same. Okay? Change to the dynamic type of RS, which is resident students. So now, if you say Jim.getTuition, it's going to call the resident student version using premium rates. Okay, that's good. How about this variable assignment here, number 5? There's a compile, right? NRS declared to be non-resident students. Jim declared to be students. Is non-resident student descendants of students? Yes, compile. So let's execute the assignments. So that one there is going to compile. So now Jim, rather than pointing to here, is now going to point to wherever NRS is pointing to. So now this will be the new dynamic type for Jim. All right. So now after this, we're going to say dynamic type of Jim is going to change to whatever dynamic type it was or still is for NRS. Change to the dynamic type of NRS, which you know is non-resident students. So the main thing for you to pick up from this example here, I'll recap, and then we'll move on to some important definition. Okay, 2 things. Number 1, when you are simply doing some variable assignments, how do you judge if the variable assignment should compile? Look at the static type. The static type of the right-hand side must be a descendant class of the static type on the left-hand side. That's what we just discussed earlier. That's point number 1. Point number 2, if all the variable assignment actually will compile, so let's now execute it and see what's going to be at the runtime. At the runtime, you can see we're going to change the pointers around. Whenever you're doing a variable assignment right here, I know that after this assignment, Jim and RS, they will point to the same objects. That means whatever the dynamic type RS is not going to change to be also the dynamic type for Jim, which is RS. So you can see how the dynamic type for Jim is going to modify. It's going to be modified as we go for different variable assignments. Okay, you just got to trace the code. All right, so 2 things. Okay, all right. So guys, how about this one here? Is this fragment of code going to compile? Let's do it quick. And before I give you some important definition. We have time, so pause a little bit. Daniel, go ahead.
The first line is not going to compile.
Because?
Because Jim uses students, which is not the descendant.
Okay. Okay, so hopefully guys you have seen that. Okay, I'll do 2 versions. Let's hand wave. Jim declared as students right here. Is students a descendant class of the static type for RS, which is resident students? No, it's not a descendants. Not going to compile. It's not going to compile because Jim's static type, which is students, not descendants of RS static type, which is resident students. And another way to put about not descendants of, the consequence is cannot fulfill the expectation of. All right. All right, let's now move on. Okay, so let's now define the two terms a little bit more thoroughly. So polymorphism, dynamic binding, they're still consistent with the intuition that we spoke about last Wednesday. Okay, okay, polymorphism and dynamic binding. Okay, so I believe it's from Latin, but I got very limited knowledge, but at least this one I look it up, right? Poly simply means many or multi, many. And morphism means shape. And in our context, shape simply means dynamic types. So polymorphism in our context simply means when you declare a reference variable to be certain static type, at a runtime, that variable may have multiple dynamic types as we go. For example, once we declare a variable of static type students, then it may have multi-possible shape at the runtime. It could be resident students, could be non-resident students. Similarly, if I declare a smartphone of static type, let's say just smartphone, in that case, at runtime, I got so many choices that can be as long as they're descendants, right? So that's really about polymorphism. Okay? So it's really about multiple possible dynamic types. Okay? So now from there, each dynamic type may have its own version of the method. So each dynamic type may just choose to override the method that it inherits, right? In that way, we want to know which version of the method should be called. That's why the consequence about polymorphism is you have to deal with it using dynamic binding. So here, when you think about when you got each dynamic type may have its own version of method, to deal with it, we need to use the principle called dynamic binding. Okay? Right here. Dynamic binding, that's something we have spoken about many times. The version of the method that's going to be called depends on the dynamic type. So this example here, we have done that so many times, right? Changing Jim from resident student to non-resident student, right? Let's look at a new one. How about that? Very quickly. Let's look at this one. Okay. So here we got SP1, we got SP2. Okay. And also we got iPhone 13 Pro, Galaxy S21. Let's visualize that quickly. So SP1 and SP2. SP1 and also SP2. So we got SP1 pointing to, and this will compile because this is a descendant class of that. And also this is a descendant class of that, right? Quick check. So SP1 will be iPhone 13 Pro. SP2 points to another object dynamically, which will be Galaxy S21. Okay? So now, if we have, let's say, if we say sp1.surfWeb, right? Surfweb is actually a method that comes from the smartphone. So that should be an expectation, right? But we don't know which surfweb it is, because surfweb could be the one from iOS, which is going to use for Safari, or could be the version for Android, which is going to use Firefox. We want to figure out which version he's going to use, right? Let's now take a look. Now, if I say sp1.surfweb, which version? Safari or Firefox? Because iPhone 13 Pro. Okay, so now dynamic type. You can think about this guy here. It's a SP1. Dynamic type of SP1. So now if you want to see, so here iPhone 13 Pro itself doesn't really define the surf web, but if you go up right here, that's the surf web, the closest one. That's going to be overridden, okay? So this one here is going to use the version from iOS. And let's now do one variable as reassignments. Give me 2 minutes and I'm done. Okay. So let's say here, if I say SP1 equals SP2, you guys can justify to see if that one will work. It will, because the static type for this one here, SP2, is a descending class of that. Okay, so that's something you can check. Well, actually, their static type is simply these two, so they will work, right? After this one here, I'm simply going to get SP1 rather than pointing to here, is now going to point to SP2. So now the new dynamic type for SP1 should be Galaxy. So now this surf web over here is going to call the version from Samsung right here. Oh, sorry, Android. Beg your pardon. Right? It's a new dynamic type. Okay, so I think I should really pause over here. So before Wednesday, so please take a look at that. And then I think we're now done with all the variable assignment. We'll go on to thoroughly about typecasting on Wednesday. All right, thank you, and I'll see you on Wednesday.